Hello everyone, welcome to EEE 366 Microprocessor Laboratory. Today I will be demonstrating the first portion of experiment 7, which is the controlling stepper motor. In this experiment, our main objective is to study and control of stepper motor using ATmega32. So these are the components that we will be needing ATmega32, and to control that stepper motor we will be needing a motor driver, and the motor driver for this stepper motor will be using ULN 2003, and we also need some connecting wires. And in case of the simulation experiment, actually we need ULN 2003A. This is available in Proteus by default, so we can use this. So now what is a stepper motor actually? So in case of stepper motor, it has multiple toothed electromagnets and it's arranged around a central gear, and it has some certain position, or I can say certain coils. Let's say it has 4 coils marked at A, B, C and D. So whenever we energize on coil, it attracts the gear's teeth and aligns them. So let's see its operation here. So let's say this is the stepper motor. It is stepping to a new position and also it is rotating. So this is how stepper motor works. So we have connection to 4 coils, let's say A, B, C, D, 4 starter points. So whenever we will energize that particular coils, our rotor will go on that particular point, through which we will be controlling our stepper motor. So let's move on. So by this process we will be turn on and off of this 4 position, and we will be controlling the rotation. So we will be observing later, don't worry. Now this is the motor driver IC. So in previous experiment I already mentioned that why do we need motor driver, because in some cases this motor takes substantial amount of current, but the ATmega32 microcontroller or other controller board can provide that much amount of current directly. That's why we need driver to provide required amount of current and also voltage. So for controlling that stepper motor we will be using ULN 2003 motor driver. So here we will provide 4 pins from our ATmega32 microcontroller in this in-on, in2, in3, in4, and similarly we will connect our stepper motor in this portion actually. So whenever you will be using an hardware, you probably notice this sort of configurations, but in case of simulation we will be observing something little different, but don't worry. And this is the power portion, and this is the positive terminal, and this is the ground. So we will be needing to connect 5 volt to 12 volt, and obviously this voltage requirement depends on different stepper motors. So let's say our stepper motors will work on 5 volts. So then we will be connecting 5 volt here, and we will be connecting in ground with the microcontroller's ground as well. So this is a typical motor driver. This motor driver basically providing required amount of current and voltage for the motor, and we can't directly connect the motor to the microcontroller because motor may need higher amount of current and voltage, but microcontroller can provide it. Now the rotation controlling. So this is our whole configuration. We will be connecting our ULN 2003 in 4 pins, and we will be using port A. So A0, A1, A2, A3, these 4 pins are being used, and they are connected to in-on, in2, in3, in4, and the motor is connected to the output port as shown here in this figure. And then obviously we need to supply some external power source to ULN 2003 in hardware, but in case of simulation we don't need this. So this is the Proteus schematic that we will be drawing in Proteus. So first of all, these are the components that I need. First of all, ATmega32, then motor stepper. So to take this stepper motor you need to search as motor stepper, and you can take this one, motor stepper. And also I previously mentioned that ULN 2003 is not available in Proteus. That's why we will be using ULN 2003A. So this looks like this. So we have 7 inputs, and we will be needing first 4 only. So we'll be connecting first 4 to our port A of our microcontroller at Mega32, and then here also we will be connecting just like this. So previously I mentioned that we have 4 points A, B, C, D. So in case of simulation, we may denote them as, let's say this one is A, this one B, this one C, and this one D. You can also denote them otherwise, then you need to program your code in that way. So I will be denoting them A, then B, then C, then D, and then I will write the necessary codes. So let's move on to Proteus. So I already drawn this, so you know that you can pick some components, like whenever you press on this P or P in keyboard, then you can pick components. So for motor, I already mentioned that you need to write it stepper. So if you write it stepper, then this motor stepper, this one animated unipolar stepper motor, you will need this. Then you also need the Atmega32. So I think you already know because you have done some experiment with it, and Atmega32, and then the ULN 2003. So ULN 2003, if you write it, this one, high voltage high current Darlington transistor array. So it is basically providing high voltage and current, nothing else. So here Darlington pair exists. Anyway, so here I basically shifted this, that's why port A is appeared here. But at first, if you take Atmega32, then probably you notice that port A exists in left side, but don't worry, I just use this X mirror. So if you like this, previously it was just like this whenever you first take, then if you press on this X mirror, then you can have port A in this right side. So now the connection, I think you can connect it by observing this, and I also showed it in your lab sheet, so don't worry. So here as I mentioned, we noticed them as this one A, and this one B, and this one C and D. So this A, B, C, D are connected to 1C, 2C, 3C and 4C, and the middle portion, this one are shorted, and we will need to supply 5 volt here. And to take this 5 volt, you can go to here in this terminal mode, and then this power. So whenever you click on this power will be available, and you can press, and then you can connect them. So by this process you can take all these components, and then you can connect them as well. And you already know that you need to write code in Code Vision AVR. So let's move on here. So now the code, first of all, this one already you know, so let's move to here. So we are defining two functions, one is half step and another is full step. So first of all, what is step? So previously I showed you here. So this rotor is rotating, right? So from on portion, let's say this is A, so from A to from B, this is called full step. So for having a 360-degree rotation, you may have 4 full step. So whenever you provide 4 full step, it will having a 360-degree rotation. So each step consists of 90 degree, since here 4 pole exists. So for 4 pole, we have step size of 90 degree. So whenever we will be rotating at each step of 90 degree, we will be calling it full step. And we also control at an angle of 45 degree, we will be calling that half step. So how that works? So first of all, we know the sequence is DCBA. Why DCBA? Since we have connected, if you notice here, so this is A, B, C, D, right? 1C, 2C, 3C, 4C, these are A, B, C, D, and we have connected A to PA0, B to A1, C to A2, and D to A3. So obviously I can say in our code that this last 4 bit, in this last 4 bit, the last bit obviously A, and the second last bit is B, and this one C, and this one D. That's why I have written it as a comment, the configuration is DCBA. So in half step, let's say I have energized as only D is active. So you can understand that whenever only D is active here, so whenever only D is active, that means the rotor will be just like in this direction, right? So the rotor will come to at point D, and after that energizing of D, we have given 1000 millisecond delay, then we have energized DC together. So now D and C both are together energized. So now rotor will be in the middle point of this D and C. And then we have given another 1000 millisecond delay, and now it's again at position of C. So now C is energized. So obviously now the rotor will be here. So by this process, we are rotating the rotor in half step, because full step was from this point to this point, I can say. So we are having a half step. That means it may need 8 steps to have a full 360-degree rotation. So by this process in the code, let me mention again. So first of all, we have turn on only D, this one, and then we have turn on D and C, then only C, then C and B, and then only B, then B and A, then A. So we are shifting our points, and by shifting our points we are mainly following this scenario. We are shifting the energization, because whenever you provide a 1 in that port, then that pin will be activated. That means proper voltage supply will be given to that pin. That means it will be energized. So by this process we are having a full 360-degree rotation, and we are doing it half step. So in this main function, that is our void main, this DDRA 0x0. Why? Because we have used last 4 pins of port A, right? Last 4 pin, that means A0, A1, A2, A3. So if you write it, so it will be 0 0 0 0, then on. So last 4 pin are on, since these are at output. So if you convert it to hex, so this will be 0F. So that's why this is DDRA 0x0F. That means only last 4 pins of A has been used as output pins, and then port A equal to 0x00. That means just the initialization, and we have given 0 to all ports. Now we have a while one. That means we have an infinite loop, and in this infinite loop, let's say we have executed it half step. So if I build all, so now build all project, so no error, no warning. So let's move on to Proteus. So we'll be observing half step at first. So that here we need to double click, and here we need to show our hex file in this program file. So we need to click on, and then obviously that whenever you have put that code vision project, there will be a debug folder, and in that debug folder you have a exe folder, and then within that exe you should have a hex file, and the hex file name you probably already given the project name. So I have written at lab 7 stepper. So this is the hex file. Now if I click on open, so this is given here in program file, and also in this CKCL fuses you need to select this external crystal high frequency, the last one, and you need to mention it 16 megahertz, just like this, and then you need to click OK. And now if I click on this, run this simulation, so if you notice here it is rotating. So if you notice that it is rotating at half steps. So whenever these two are energized, so here, so let me show you from beginning. So let's say this is the initial state, and now click on here. So this was D, right? So now it is D. Now D and C, now it is only C portion, and now it is C and B middle portion, and now it is only B, and now it is middle portion of A and B, now it is only A, and now it is only starting point. So by this process it is having a half step, and it is having a full 360-degree rotation. and this ABCD I just considered them just like this ABCD. You can consider them as otherwise also, and then you need to configure your code as that portion. So I think you understand that we are having a full 360-degree rotation, and we are having a half step. If you notice, in each step we are having a 45 degree. So 180, now 270, now it has a 315, so 45 degree. Now it is 360, that is 0. So now it is 45 degree. So and each step it is having a 45 degree. That means it is finding a half step. Now let's move on to our full step portion. So obviously in full step we may proceed as follows. So first of all, in this full step function we have energized both D and C. So we have energized both D and C. So obviously the shaft position will be just like here in the middle position, here in the middle of D and C, and then we have energized in the middle of C and B. If you notice in the code, so here now it is on C and B, both are active. That means the shaft will be in the middle position of C and B, and then it has moved to middle position of B and A, and at last it will be the middle position of A and D. So by this process we will be having a 90-degree shift. So now if we execute that full step portion, so I can uncomment this one and I can comment this one. So now this will execute the full step function. So now if I click on this build all project, again no error, no warning. So let's move on here, and since we will be using the same code, so it is already loaded. That's why you don't need to load the hex file again. So if I now click on this run the simulation, probably you noticed here it is having a 90-degree rotation and edge time. So let's say this is the default step. Now it is 90 degree, then again 90 degree, again 90 degree, and at last it is again 90 degree. So it is having a full 360-degree rotation and 90-degree rotation at each time. That means at each step it is having a 90-degree rotation, and we denoted some points. These are A, B, C, D to demonstrate you more clearly. And also again and again I am mentioning that this portion and these pins that I mentioned, A, B, C, D, these are not fixed. I have defined them just like them, and similarly I have configured our program here our program similarly to that ABCD denotion. So by this process you can have a half step or full step, and by this process actually the stepper motors can be controlled. So whenever you need fixed controlling of your shaft, you can use this. So you can understand that we have used a for loop. That's why it is having a rotation, and also we have given 1000 millisecond delay. So if you reduce that delay, so obviously this rotation will be faster. And let's say you want a particular position, let's say 180 degree. So obviously at that point you don't need a while loop, so you can just write fixed portion, let's say this one. All I am saying that if you write it this portion here, let's say, and no half step, no full step, so we are just having a at this portion where A and D both are active. So let's build this. Okay, let me show it. Let's build it again. Okay, no error, no warning. So now if I click on here, so if you notice that A and D, so by default it is the default position. So let me take it another position, let's say this one. That means A and B. Oh, I think I have missed something. So last 4 bit, this and then again last roll bit. Okay, so now build all project. So no error, no warning. So now if I stop and then if I run it again, so now if you notice it is between A and B, so it is just minus 90° point. So by this process, you can have a precise control in your real life projects. So thank you. I can end it here.